You know, in any craft, whether you're a carpenter or a chef, choosing the right tool is absolutely everything. It's the difference between a masterpiece and a total disaster. And in organic chemistry, believe me, it's no different. Today, we're going to dig into a classic choice every chemist faces, but we'll frame it with a simple question. Seriously, when would you use one over the other? You're going to grab a sledgehammer for brute force, right? You need to knock down a wall, you're not worried about being gentle. But for delicate, precise work, like tapping in a small nail without marring the wood, that's when you need the finishing hammer. Well, it turns out chemists are making this exact same choice all the time. Not with metal and wood, but with molecules and reagents. They have their own versions of these hammers. And knowing which one to pick, well, that's a critical skill. Okay, let's get into it. So here's the plan. We're going to meet a chemist's two favorite hammers. We'll compare their power versus their precision and see how they actually work. Then we'll put it all into practice with a real-world molecule. After that, we'll expand our view to the whole modern toolbox and finally talk about why this choice really matters for your career. All right, first up, let's meet our chemical hammers. We're talking about two of the most famous, most common reducing agents you'll find in any organic chemistry lab. In this corner, we have lithium aluminum hydride, or LiAlH4 for short. This is our sledgehammer. It is an incredibly powerful, reactive, kind of scary tool. And in the other corner, we have sodium borohydride, NaBH4. This is our finishing hammer. It's way milder, much more selective. Now, the real difference in power comes down to the bond holding the hydrogen. With lithium aluminum hydride, that aluminum-hydrogen bond is weaker. It's more polarized. It makes that hydrogen ready to leap off and attack. That's what makes it such an aggressive, powerful sledgehammer. Okay, so we're throwing around these words power and precision, but what does it actually mean when we're talking about chemicals? Well, it all comes down to what they can react with, and more importantly, what they can't. And this table, wow, it really lays it all out. Check it out. Both of our tools can handle aldehydes and ketones, no problem. They'll turn them into alcohols. But then look what happens. Our finishing hammer, NaBH4, it stops right there. It's selective. It won't touch those more stable groups like esters or carboxylic acids. But our sledgehammer, LiAlH4, it just plows right through them. It is so powerful, it will reduce pretty much any carbonyl you throw out. You know, sometimes the simplest explanations are the best. As one Reddit user so beautifully put it, lithium aluminum hydride is a much stronger reductor. I mean, that's really it. That's the core difference you have to burn into your memory. So what's the actual job these tools are doing? It's something called a hydride reduction. All that means is they are delivering a hydrogen atom that's packed with 2 electrons. We call that a hydride ion. And its mission is to find a carbon-oxygen double bond, a carbonyl group, and transform it into an alcohol. So how does this magic actually happen? Let's take a quick peek under the hood and see the mechanism. See how these reagents actually get the job done. It's really a beautiful, classic two-step dance. First, that hydride ion, which is just desperate to give away its electrons, sees the carbon in the COO group and just attacks. It forms a new bond. That creates this intermediate with a negatively charged oxygen. Then, in step 2, you just add a little bit of a proton source like water to neutralize that charge, and poof, you've got your final alcohol product. It's simple, it's elegant, and it's incredibly useful. Okay, enough theory. That's how it works on paper. Let's see how this all plays out in the real world, in a lab where a chemist has to make a tough, strategic call. So check this out. We've got a plan here to make this pretty complex molecule. The first step builds the main skeleton, but it leaves us with a ketone, that COO group. Now, the second step is a reduction, but here's the twist. The goal isn't just to make an alcohol. The goal is to completely obliterate that oxygen atom. Get it out of there. So now the chemist is at a crossroads, right? You've got to get rid of that ketone. The question is, which specific reduction method, which tool is the right one for this particular job? And it's not as simple as just picking the strongest one. And this is where the real art of chemistry comes in. To get rid of that oxygen completely, you need specialized tools. Two classics are the Wolff-Kishner and the Clemmensen reduction. Now, the choice here isn't about power, it's about compatibility. See, the Wolff-Kishner uses a strong base, while the Clemmensen uses a strong acid. So the chemist has to look at their molecule and ask, is there anything else on here that's going to get destroyed by acid or by base? The right choice depends entirely on the context of the whole molecule. But here's the thing. The story doesn't end with just a couple of hammers. The modern chemist's toolbox is just massive, and it's always growing, always driven by new priorities like sustainability and efficiency. And a huge new player on the scene is catalytic hydrogenation. This is considered a green process because it's super efficient with its atoms. It makes almost no waste. Instead of using up a chemical reactant that you have to throw away, you're using hydrogen gas and a reusable catalyst. That is a massive advantage, especially when you're working on an industrial scale. And if you're wondering why big companies are so into this, well, here's a big reason: money. It's not just about saving the planet, it's about saving a ton of cash. One study showed that by cutting down process waste by about half, companies saw a whopping 65% in cost savings. Being green is good for business. And you gotta remember, we're not talking about little beakers in a lab anymore. These reactions are being run in these gigantic, building-sized industrial reactors, turning out tons of product. At this scale, every single choice, what reagents, what solvent, what temperature, has enormous economic and environmental consequences. Okay, so let's tie all of this together. Why does understanding this decision-making process matter so much? Because, frankly, it's what separates someone who just knows chemistry from someone who is a professional chemist. I want you to imagine you're in a job interview for a chemist position. They're going to ask you stuff like this. See what they're doing? They're not asking you to just recite a fact. They're asking you to explain your choices, to defend your strategy, to show how you solved a problem. They want to know if you can pick the right tool and, more importantly, explain why it was the right tool. And that's really the big takeaway here. Mastery in chemistry isn't about memorizing 1,000 reactions. It's about developing that intuition, that critical thinking to look at a problem and choose the most elegant, efficient, and appropriate solution from this massive toolbox of possibilities. And that really leaves us with a big, exciting question for the future. We've seen the toolbox evolve from simple hydrides to greener, more sophisticated methods. As we keep pushing for chemistry that's more sustainable, more powerful, and more precise, what new skills, what new knowledge, and what incredible new hammers will the next generation of chemists need to invent,